Hello, my name is Bill Goble from Exida, and we're going to start part 2 of our 4-part series on getting good failure rate data. In part 1, you learned that there are some people who don't believe in probabilistic analysis. You learned what's a failure rate and how to do a point calculation. In part 2, we're going to talk about field failure data and the requirements for field failure data, quality field failure data. We're going to talk about field failure data sources, and we're going to talk about estimation limitations. Reliability engineers have known for decades the whole foundation of reliability engineering was the collection of field failure data. And of course, we've all known for decades that's the ultimate source of data. IEC 61511, the 2016, the new version, 2016-2017, even has some pretty strong language talking about the need for high quality, realistic field failure data. So take a look at these requirements. Credible, traceable, documented, and justified. Why would they put that strong language in? It's really important that the data you use in probabilistic calculations be realistic. One of the primary and original techniques for getting failure rate data is a group of methods called failure rate estimation. Failure rate estimation is when you gather up field failure data and you use statistical techniques to estimate what the expected value of the failure rate will be. Been in use for many, many decades. Now today, the most common techniques are categorized in 3 groups. Industry databases, where some consortium gathers up data and uses top experts to analyze it. End user field failure rate studies, where individual companies will gather up their own field failure data and analyze it. And lastly, manufacturers' field return data. Manufacturers have warranty return systems and field failure return systems. And there is a lot of valuable data in there, but you do have to be careful about that one. Industry databases. Consortiums exist in the process industries. The OREDA database, the Offshore Reliability Equipment Database Association, OREDA, gathers up failure data from offshore platforms in the North Sea. And there are a number of different companies supplying this data. It's sent into Trondheim University, a company called Syntef, who has a large group of experts, and they are producing very high quality data for the process industries. I can't thank them enough. But the data is significantly aggregated. It means, for example, they will give us data on a valve assembly, which has pneumatic control components. It has an actuator. We don't know what kind. It could be Scotch yoke, could be pneumatic, it could be hydraulic, and a valve. We just don't know what kind. Might be a butterfly, might be a ball valve, might be some other type. But we have a good, high-quality data point for this collection of devices. I'm glad we have that data. End users will also do their own field failure rate studies, and some end users have a good quality system in place, and some don't. Some end users have experts who know how to analyze the data, and some don't. So the bottom line is there's a significant variation in data quality, but there are some shining stars out there who are giving us very useful pieces of information. Lastly, the third estimation type is the manufacturer's field return studies. Now, I worked for a manufacturer. I was taught how to do these studies, but quite frankly, I was taught to make the company look good, all right? The manufacturer doesn't know all the failures because only a small portion are reported back to the manufacturer. I've done surveys, I've asked end users, do you send all your failures back to the manufacturer? Oh no, we throw them away. The failures that come in the door are tested. A test fixture, and they say, I can't see a problem. No problem found. Or customer abuse. No warranty. They aren't counted. The end result is we've already made ourselves look a little better than we really should, the manufacturer. Then, of course, how many operational hours are in the field? Many manufacturers say, I shipped it, and it probably goes into use a week later. Well, maybe not. What if it sits in a storeroom for 6 months? What if it sits waiting for other pieces of equipment for 6 months? So a manufacturer has to make a lot of assumptions, and that's what I was talking a little bit about in part 1. But there's still valuable data there, especially when the failures are traced down to root cause and when upper bound and lower bound numbers can be established by varying the assumptions. Failure rate estimation techniques. Let me give you an example. I got a data sheet from a manufacturer. It's here in gray. And they gave me warranty data calculations for a series of electronic modules. Let's focus on the controller, the logic solver module, and according to their field-proven MTBF is 92.28 years, or 1,237 fits. Okay, my first guess is this is probably an optimistic number, but we'll come back to this later. A mechanical manufacturer gave me a set of data so we could use it in a safety calculation. This was a pneumatic Scotch yoke actuator. And I go through the numbers. They use a confidence level of 90. 90 is pretty good. Assumed, blah, blah, blah. Dangerous failure rate, 17.3 fits. 17.3. How'd they calculate that? What assumptions did they make? I don't know. None of that's in the report. At least I couldn't find any in the reports we were given. So my assumption is, my going in position is to be skeptical and assume this is a bit low, but we'll come back to this later. Now, I'm not saying you can't do a good job with estimating failure rates. However, you got to remember I was at an OEM equipment manufacturer, and the engineering manager said to me flat out, I can hire a statistician to give me any number I want. Oh boy. Any number I want? Well, how do they do that? Well, it's easy. What assumptions do you make? Yeah, you're getting the picture. If you understand the equipment operation, how it works, if you understand the component failure rates, if you understand the key environmental variables, you understand how equipment is used, the application, and you know how the data will be used by engineers, you can do a good job making assumptions, and one can do a good job estimating a failure rate. But if you don't do these things, you're not going to get an accurate or realistic number. I like to say math alone is not enough. Some people think it is. Sorry, it isn't. You know, this whole estimation thing was really easy to do decades ago. I remember when I was growing up, products had vacuum tubes. Anybody remember vacuum tubes? Well, there's still some products around that have them, but they look like this. They failed a lot. There were hot heating coils. They would burn out. It felt like they would burn out right in the middle of my favorite TV show in our new color television. But of course, really it was maybe once or twice a year. But that's a lot. Everything has changed. The quality is up. Designs are stronger. Everything has increased, and now it's much, much harder to keep track and to do failure rate estimation. Doesn't mean it's not valuable, it's just truly harder right now. So estimation is hard to do, and there's another problem. How old are those products on the North Sea offshore platforms? I don't know when they were installed, but it's probably not a big population of the latest design. What's the point? Estimation techniques do not give us data on a new design until a great period of time has passed. And it's been that way since the early days of reliability engineering. Early on, everyone knew we had to have something better than just estimation. In part 2, we talked about failure rate data, the requirements, estimation techniques, the 3 main sources, and estimation limitations. Estimation. It's harder, it's not timely, but it's still valuable. I hope you've enjoyed this part 2. There's a whole lot more excitement to come in parts 3 and 4. We'll see you then. Bye-bye.